The only thing I can.
Would diverge.
Nice, it would diverge. So, Shujosh, what are you saying?
I also want to say diverges. Like we wouldn't get the solution.
Yeah,
It
exactly.
wouldn't convert. So
Yeah, so we would get infinite norm, and therefore we expect omega to be convergent, and therefore we can take a series ansatz for omega, right? Okay, where n cannot be negative, because if n was negative, if n were negative, we would get things diverging at the origin, right? And we know that can't be in the case. Okay, so now suppose that instead of omega, we now have we deal with the function v of r, which is say which is r to the power L plus 1 and omega of r. Okay, in other words, if I were to say u of r is v of r times e to the power minus kr. Okay, so this is the definition. Or you could take this as the definition. Then this series would be replaced by a different series, which would be v of r. And now n doesn't start from 0. N starts from L plus 1. And it goes all the way to infinity. In an r to the power n, okay? So this is going to be our ansatz. Now, if I work out what the equation is for v, we get d squared v by dr squared minus 2k, k remember is square root of minus e, dv by dr plus 2r by r, and then minus L plus 1 by r squared v is equals to 0. Okay, so this will be our differential equation then. Now, it's a generic ODE. We can solve it by using the usual series method and then we can derive a recursion relationship, and you can show that the recursion relationship is an plus 1 is equal to 2 nk minus 1 divided by n plus 1 minus L plus 1 an. Okay, so this is the recursion relationship. So once that we have a recursion relationship, what do we want to do? We want to understand this asymptotic behavior, right? We want to understand what kind of solution do we get for large values of r. Of course, for large values of r, we see that the terms that are going to dominate are the terms with a large values of n, right? So for large values of r, we want to look at what this looks like in the limit where n goes to infinity. And in that limit, an plus 1 over an, the ratio of the coefficients, is 2k over n. So if I look at the large, the large numbers, the large terms, the large values of n for large values of r, then in the limit where r goes to infinity, this v of r is going to be an exponential of plus 2kr, right? Is this clear how this comes about from this thing? Well, it just, just look at the series, right? An r to the power n, and this is n. An is going to be an is going to be what? An plus 1 is this number times an. So it's 2k n plus 1 n 2k n minus 1 dot 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 dot, right? R to the power n plus 1, right? So this is basically nothing but 2 to the power k to the power n divided by n plus 1 factorial. Well, I think there's a plus 1 here. Yeah. R to the power n plus 1. So this is e to the power 2kr. Okay. Okay.
Yes, sir.
Yeah. So we see that for large values of r, this is going to diverge, and therefore, here we get 2kr. Whereas if I look at my full solution here, we get minus kr. So 2kr is going to dominate minus kr, right? So we are going to have diverging solution, unless for some value of k, the numerator vanishes, right? Some value of n. You agree, right? Then this series terminates, and we don't have this asymptotic behavior no more. Well, we will have this we won't have this asymptotic behavior anymore. So k has to be equal to 1 over n. If I square this, I get e of n is minus 1 over n squared. So we have our energy quantization condition. Now, if I restore h, e, m, etc., well, we are, if I now, then e of n just becomes minus m e to the power 4 divided by 2n squared h squared. And now remember that the value of n is that n is always greater than L. So whatever L is, n has to be at least 1 more. Okay? So if I fix a value of n, then L will go from 0 to ... n minus 1. Okay? So in this equation, this is the important equation. N is called the principal quantum number. Because it determines the energy. And L is the orbital angular momentum, orbital angular momentum quantum number. And and m is the reduced mass. In chemistry, they have their own notation, L01. If L is 0, okay, sorry. So what I wanted to say is that in chemistry, they have names for m, which is the, okay, so this m is the reduced mass, and this m is the z value of Lz, okay? Maybe I should use mu here, okay? But from the context, it should be clear. So in chemistry, they say that they have a notation called SPDF. Are you guys familiar with this? This is like 0. This is, I think, 1. I think this is 2. This is 3. I think these are the values of Z. Anyway, we are not going to use that. So in MKS unit, okay, let me make some comments now, okay? But before I make any comments, are there any questions about all of this, all the derivation here? I mean, it's pretty easy, but still.
I couldn't quite get that e to the power 2 kr part where it came from.
All right, sure. Yeah, so this is basically, you got this though, right?
Yes.
Yeah. So, so the idea is that, this is our ansatz. Sorry. So if I take very large values of, say, k, n in this sum, then what, suppose I take one of the terms here, say n equals 2, say k is not a good thing, n equals to, say, I don't know, p, where p is large. Then what is that term going to look like? We're going to have AP, RP, right? But what is AP? AP is, according to this formula, is going to be 2k by p and then times AP minus 1, right? Sorry, let's take AP plus 1 here, plus 1 here. Then this is going to be AP R P plus 1, right, Nahi?
Yes, sir.
Okay. So now I can keep doing this. What is AP in terms of the smaller one? It's going to be, again, 2k divided by p minus 1 a p minus 1 r to the power p plus 1, right? So now if I then express this in terms of the smaller one and keep on doing that, I will get like p plus 1 factors of I will get down to yeah, so basically I will get down to so if well, when we get down to smaller values, these values will kick in, right? The more we have to take more exact values, right? But I'm just going to say that those are not the values which are going to dominate. So this we can write as 2k to the power p plus 1 divided by factorial of p r to the power p plus 1, right? So this up to some factor of r, I'm going to get e to the power, if I sum over everything, I'll get e to the power 2k r, okay? So this factor of r is not going to be matter, is not going to matter in the very large r limit. And now if I compare this thing to this thing, we see that because it's minus k and over here we get plus 2k, this is going to dominate. And therefore, the wave function for large values of r is going to have e to the power kr. And therefore, it's going to diverge. So the only way that it's going to not diverge is if this series ends at some point, and this series can end if this becomes 0 for some value of, given some value of n, there has to be a k such that this is 0. And that condition is this condition. And that condition leads us to the quantization of energy. Okay?
Okay, sir.
All right, so any more questions?